Oh, um, okay, so somebody wants the link for recording, but it's, how do I get this? Then I need, the Zoom link. Okay, I'm a bit confused. So, a link of YouTube I don't have yet. I mean, it's a bit complicated to get it now because I need to set up VPN and so on. So I just sent the Zoom link on Telegram. Okay, so let's remember what we did last time. So we discussed again about kernel for vertex covered problem. So you remember vertex covered problem. So there was a graph and there was a minimal node so that every edge of the graph has an endpoint in the set of nodes. Everyone remembers, right? So, and then we explained that there was a kernel of size with k squared plus k nodes. That means that there were a set of rules and we could drop nodes from the graph and only keep k squared plus k nodes so that the problem is equivalent. So we drop nodes and decrease k. There were these rules. And now there was a killer rule where we can go from k squared plus k to 2k. And this was by using a reduction to linear programming. And such reduction is important for optimization algorithms also. If you do a certain, there is a branch and bound technique. I don't know if you learned in other courses. So when you do big searches for optimization, so then you organize a search in a tree like we did, the branching tree. And then there is a technique like to cut off branches early. And what they do is sometimes use a bound from linear programming to say this branch of the tree will not help us, will not provide, they want to early detect this. And so how does it work? Well, we have a graph and we want to know whether it has a vertex cover of size k. So here is our input for the vertex. So we will write this as a binary programming problem. That means that we can use linear inequalities. We write this as a set of linear inequalities over binary variables. So what we do, we create a variable. So let's give the nodes names, A, B, C, D, E, and then use variables XA, XB, and so on till XE, and assign and require that they have binary variables. Now we need to select a set of vertex cover problem solution is a set of nodes, and we encode this set by assigning zeros and ones to the variables. So, for example, the set A, D, C corresponds to setting this to 1, 0, and so on. And now we can write the requirement that our encoded set is a vertex cover corresponds to a set of linear inequalities. For example, the set AB, the edge AB needs to be covered, means that XA plus XB is at least 1. And so we write down a requirement for all edges. XB plus XB should be bigger than 1, and so on. XE plus XC for example, bigger than 1. Okay, and so there exist solvers, like there is the software mixed integer programming mixed integer linear programming, MILP solvers, you can give them the set, and then you ask for integer solutions. So in the solver, you need to add inequalities that XA is between 0 and 1, an integer. So it searches for integer solution. But this solver can be very slow because you're solving NP-hard problem. So that means if you encode some task from crypto in this way, so you apply reduction to 3 set and then get from 3 set, you get such inequalities. Then, of course, your solver will work very slowly. However, there exist linear programming solvers that give fractional solution to the variables, and you can ask for a solution. And they are theoretically guaranteed to work in polynomial time. So they will give a solution. Okay, sorry. And I forgot one requirement. We never used K in the set of inequalities. So what is the remaining requirement? So when we are using binary linear programming, one requirement is missing. I forgot to write it. That uses K. So we need to require the vertex cover is of size at most K. So you're not, and yeah, sum, exactly, yeah. XA plus XB plus XE is at most K. So that's our, so in this case, we have 6 edges and 7 inequalities. So for programming, it's kind of annoying because you have to write it as matrix. So X will be a vector, A will be coefficients of this thing, and you require this smaller than B. So note that here we have bigger than, but we can negate to get smaller than. Okay. So, so what can we do? We can ask for, in linear programming, we can ask for an objective function and minimize it. And so we can ask for the solution with fractional solution for the variables that minimizes this sum. And when we see that the fractional solution, the minimal value here, is strictly bigger than K, we know the answer for our problem. Because fractional solution will always be smaller. And so there is the example of a triangle. And so the minimum fractional value of the vertex cover for a triangle, it is, and so integer, so normal vertex cover minimum size is 2, but fractional value will be smaller than 2. And we can have 2, so when we put all nodes to 1/2, then XA plus XB is 1, and so on. So the fractional value is smaller. So it can happen that you're not lucky, and if you minimize this, you find something bounded by K or even smaller than K. Then there is no solution. However, we can do something else. So we can identify 3 sets of nodes. So they are the sets V0. So the problem is with the new markers are very thin, and it might be hard to read. But here the image looks quite good. So so we will have 3 sets of nodes in our graph. We call them V0, V1, and V1/2. So they are the axis, the nodes whose x value is exactly 1/2 will belong to this set. Those who are more than 1/2 are come in this set, and those who are less than 0 come in this set. And so what is the new kernel rule? And remember, we had kernel reduction rule. Nodes of degree 0, we throw away, we don't need to do anything. Nodes of degree 1, we throw away and add the neighbor to the vertex cover, so we decrease K by 1. And now what we will do is we will throw away this set, all nodes whose fractional vertex cover, optimal fractional vertex cover is smaller than 1/2. We can throw them away. These nodes will go in the vertex cover. So we decrease K and delete the nodes. So decrease K by the size of V1, delete the nodes. So they are also gone, and these nodes are left. So this is Nemhaus-Strotten theorem, the sense that if you do this operation, your problem remains equivalent. So let me write the rule. So the cut rule, delete V0 and V1, and k goes to k minus the size of V1. So this is the last rule. Now there is one more rule. What we are left with are all nodes that have a value 1/2. So if k is smaller than half of v, of the size of v, then we have no answer. Sorry, if k is... So if k is smaller, yes, if k is smaller than 1/2 of the size of v, we have no answer. Second rule, if k is smaller than the size of v1/2 divided by 2, answer no. And this is precisely by the rule. All nodes of v1/2 by definition have fractional value 1/2. So we will need at least 1/2 of this size to cover everything. So what does it mean? That after this reduction rule, we have k bigger than size 1/2 over 2, and the size of v2 is the size of our problem. So in other words, the remaining size of our problem is now bounded by 2k. That's why I say, after applying the two last rules, we have kernel of size at most 2k. So we improved from k squared plus k to 2k. Yes. Yeah. Okay. And then, okay, before I prove it, let's discuss further. So people tried 1.9k, but nobody knows if you can have kernel of this size. But people know that you cannot have kernel of size k to the power 1 minus epsilon. I keep forgetting what is. So there exists a theorem. I forgot whether it's a linear coefficient or in the power. But it's proven that this is not possible unless some conjecture and computational complexity is false. It's collapse of time hierarchy theorem. So it's a generalization of the NP problem, and somehow at some point this generalization fails, and nobody believes that this can happen. So there's probably no kernel like this. However, Lampis has found a kernel of size 2k minus c log k for every c. So if you increase c, then the runtime of the kernel is polynomial, but it's only polynomial for fixed c, so the power goes up. And this looks like the c log k looks like significant. So I quickly read the paper, but I didn't add it to the course because, yeah, it's not so easy. It's a bit too difficult, but also for the programming exercise, I need more time to prepare. Okay, so this for research. So this is only like, I think it was 2007 or 2011 or something. It's quite recent, this Lampis result. Okay. So now let us prove that this rule is correct. So if we do this, apply this rule, then the minimal size of the vertex cover remains the same. So minimal size of vertex cover should remain the same. Okay, so this is called Nemhaus-Trotter theorem. Nemhaus and Trotter. And it was invented in 1976. So then parallel parameterized complexity did not exist. It started in the 90s. But these people just invented it as just a practical way to speed up, so ad hoc way. Now we can just summarize their theorem as vertex cover has kernel of size 2k. It's kind of corollary. Okay. Yes. So let us think about the graph and some of the nodes. They have xv smaller than 1/2. Other nodes have xv bigger than 1/2. And then the last part has xv exactly equal to 1/2. Okay. So I will prove that if there exists a vertex cover, so let's take any vertex cover. And so this vertex cover can be of this form. So it can be something like this. So let's say that this is a size of optimal vertex cover of our problem. So just any vertex cover. So remember what we will prove. We will prove that if we drop V0 and V1, then the resulting problem has a vertex cover. Resulting problem has a vertex cover of size VC star. Wait, so there are two directions. So first, let us say that, okay, let's first do the other direction. So let us take a vertex cover whose size, vertex cover of size the remaining problem. So what we did in the remaining problem, we added all the elements of V1 to the vertex cover and then solved in the other problem. So imagine there is these two nodes are in the vertex cover of the remaining problem. Then we need to check that if we add these nodes to the vertex cover, all edges in the graph are covered. Okay, so now let us think where can be the edges. Can I have an edge like this? So what do you think? So what is definition of V0? No, and why? Yeah, so xv, so if you have two nodes here, their linear programming value is smaller than 1/2. But then it will violate the constraint of this corresponding edge. So this is independent set. So this is already good news. We threw away these nodes, but they internally have no edges. Okay. Now let us think again. Can there be an edge like this? Yes?
No.
So here, no, here we have exactly 1/2. Here we have less than 1/2. So these edges, we also don't need to worry about them. Okay. So, but here can be edges and here can be edges. Of course, internal edges here are okay. Edges from here to here are also covered. Okay, can there be, so we're good. So here we have no internal edges. We have no edges from here to here. We might have edges from here to here, but they are covered because we took all of V1. So which edges are there? So everything with V0 is okay. Now let us think. Everything inside V1 is okay and leaving from V1 is okay. Now we have to think about inside V2. Can there be an edge like this? Well, yes, according to these rules. So the inequalities don't forbid them. However, what did we assume here? Remember what we assumed about the set VC star. We said that VC star was a solution of the remaining problem. So VC star covered all the edges. So these edges we also don't have. So we start with a solution from this set. And then we check that all edges are covered, and it's okay because we went over all the cases. Okay, so but now we have a harder task. Now we think about any vertex cover, and we will prove that if in this vertex cover, so we take any vertex cover, and it might be something like this. Now we want to understand that in any vertex cover, if we add the non-used nodes from V1 and we remove the nodes from V0, then we have again a vertex cover. This will be the claim. So the strategy is, so we have to prove that if there is a vertex cover in the original problem, then we have a vertex cover that has no nodes from V0 and contains all the nodes of V1. And this vertex cover is bounded by the size of the original vertex cover. So that means that VC star is solution of original problem. Then VC star union V1 minus V0 is vertex cover. Is also vertex cover of original problem. And size, so let's call it S. And size of S is smaller than the size of VC star. So after we prove this, we understand that this rule is correct. So applying the rule can only decrease the size of the vertex cover because of this specific one. Okay, so first let's check that S is indeed a vertex cover, but that's the same like we did before. Oh yeah, yes, stupid, yeah, okay. So now we need to do is prove that size of S is bounded, size of S is bounded by the size of vertex cover. So let us write more carefully what we have done. We have added, so we have dropped these nodes. They are dropped, and we have added these nodes. So we need to prove that number of nodes that are dropped is at least number of nodes that we added. Okay. And so how will we do this? The plan is to think about two fractional solutions. So fractional solutions where we increase the values of xv by a little bit, by epsilon, but such that in the second solution, x prime v, we will still have that all nodes are smaller than 1/2. And so we will increase the value of xv a little bit on these nodes and decrease a little bit by epsilon on these nodes. And so we will say that xv is equal to xv plus some small epsilon. And here we set xv equal to xv minus some small epsilon. So we will note that the new solution, the total sum of x primes, can only increase because we said that this was a minimal solution. Now, this operation, let us see that it respects all the inequalities. So why does it happen? So here we increase things, but and so epsilon is small enough so that all the variables are still bigger than 1/2. So that means that any edge here internally linear inequalities are still satisfied after this modification. And so we decrease not too much. Here we don't have any edges. Here we didn't change anything. So where do we also need to check? Here we decrease, so we need to check outgoing edges from V1. So edges that go here, they are okay, because we remain bigger than 1/2 by choice of epsilon. So edges that go from here to V0, they are still okay. Why? Because x prime decreases on one side and x prime increases on the other side, so no change. Okay, so I checked from here to here internally and from here to here. So what we conclude is that this is also a solution if epsilon is indeed small enough. Okay, so we have a new solution. But this means that the sum of all x's prime v can only increase. Must be bigger than sum of xv without the primes. And this is precisely what we want, because where did we increase? We increased on this market area. We decreased on this market area. So number of increases must be at least number of decreases, because this is needed to have this inequality. And so we have proven that we dropped more nodes than that we added nodes. And this is precisely this, this equality. So it's very simple, short proof, and it's very impressive by Namhausen and Trotter. I guess they're Germans, judging by the name. I didn't check. So, okay. So now we proved the safety of our killer rule in the kernel. But unfortunately, so, well, there is something nice. So when you use linear programming, so you can, you want to maximize the number of ones and the number of zeros. And so you can, you can, for every node, try to set it artificially equal to 1 and see whether the value k changes, the optimal value of the sum changes. And in this way, you can check whether there exists some solution for which the node is equal to 1. And so you can drop all the nodes whose solution is 1, so you can probe. But there exists a direct algorithm that computes the solution with maximal numbers of zeros and ones. And it's kind of clever algorithm. So I'm not sure if you want to learn about it. I can tell the algorithm, it's pretty cool, and then you can tell me if you believe it or not. So, okay, so algorithm will, yeah, so if there are questions about this proof, then you should ask before I delete. Oh, so let us think about our input here. Algorithm will construct a bipartite graph and solve the vertex cover problem on bipartite graph. So it's really cool. And there is exact algorithm for bipartite graph. By the way, that I should have told this long before. So if you're lucky, you make a check. So in network X, you can always, there is standard algorithm to check for bipartiteness. It's built in. And if it says yes, then really cool, you get the answer from exact algorithm. So what you do is, there is theorem that says matching, you remember what is matching. It's a set of edges that's pairwise disjoint. In bipartite graph, maximal size of matching is equal to minimum size of vertex cover. And so you always have algorithm. I mean, most packages, software packages have algorithm for maximum size bipartite matching and maximum matching in bipartite graph. So many packages have it. It's quite common. So there exists algorithm for maximum matching. In general graph, it's a complicated, I mean, not so complicated algorithm, but more complex. There are different algorithms with different runtime, so it's less easy. So it's less obvious that it's in a package. Okay, so what we do is we start with, let's say, this graph, and we will build a graph consisting of 2 copies of the nodes of this graph. So here, but we don't add the edges. What we add, so for every edge, so let's say this edge here, we add, so here, there's the edge, we add a cross like this. And we do it for all the edges, we add such a cross. And then we have bipartite graph. So one bipartition, of course, left set, the other right set. So there are no internal edges. These edges I just draw for understanding. Then we ask for minimum size vertex cover on this graph, or maximum size bipartite matching in this graph. And so we get 2 values for every, so for every node here, we have 2 copies. And so this node has 2 copies. And we have 2 answers, this node in the minimum vertex cover or this node in vertex cover. And so the value that we assign to this node, and so xv will be equal to, let me write it, xv equal to xv1. So if this is v1 and v2, and here is our node v, then it will be 1/2. If it will be 1 if both of the copies are in the vertex cover, 0 if neither, and 1/2 if exactly one of them is in the vertex cover. So here we get size vertex cover, and it is vertex cover, wow. Yeah, indicator. Vertex cover plus indicator. Vertex cover. And then we divide by 2. So indicator function, it's 0 or 1, depending on whether the statement is true. So that's, so this algorithm, so you, with a bit of work, you need to create 2 graphs and then adjacency lists, and then call the maximum matching algorithm. Okay, so so then there is a theorem that this algorithm gives optimal fractional vertex cover. So the time you need for this is time to get maximum vertex cover. So there is a very robust Karp-Vazirani algorithm. And so it runs in time number of edges times square root of number of nodes. So that's number of nodes to the power 3/2. So for this application of vertex cover, this is a dream of algorithm. It will be very fast because you're doing exponential searches. Now, if you have a real world graph with big degree, then, but in most applications, graphs are sparse, so number of edges proportional to the number of nodes. And then this can be like only for really big graphs, like social network or something. With many millions of nodes, it might be a bit annoying there, or billions. Okay, so so now if you want me to tell why this is correct, I can explain it to you, but we can also go to the next topic. Or I can explain you in the end of the lecture if there is time left. Yeah. Okay. So then we are done with this one. But there is nice explanation in this book by how it's called again, by Sigan, and forming. It's in the wiki, the reference. So it's in the first chapter, near the end of the first chapter. Well, I mean, the first chapter 1 is introduction, but the real chapter. Okay, so now our problem, dominating set, which was a disaster with natural parameter. Let's change the parameter to the degree. And so there is a very nice lemma by Erdős and Rado about sunflowers. And so they will have, it's called the sunflower kernel. But first, let's speak about hitting set problem. So in the hitting set problem, so D hitting set problem. Input is parameter K and a list of sets S1 till Sn. And then the parameter is maximum size of the set. So D is equal to maximum of S1, size S1, Sn. And the question is, does there exist a set X so that X intersects every set? So it's like hitting set. It's all NP complete problems optimized. You have to hit something or destroy something. So, well, it sounds like some army, all NP problems useful for the army. So hitting and destroying. And so does there exist an X such that for all I smaller than n, as I intersect X is at least 1. So it can be like no, it's a destructive example, but it's the first thing that comes into my mind. So you have villages and you want to spread some disease and all the villages, and then there are interactions. Okay, there's so many things, or maybe some warning message that there is some danger, and you know this person will tell this person, and then so you have sets of people that can inform in time, and then what's the minimal number of messages you have to send? It's okay. I don't know. I haven't used such a problem studied in practice because I did very little practical work. So, okay, so and then we want to prove that this problem is an FPT. So dominating set is a special case of this problem. So here the sets are nodes and all of their neighbors. And in the dominating set, you want to have a set of nodes so that every node is either in this set or has a neighbor in this set. So actually this problem was in the Roman Empire. There was a rule that so there has to be armies in the villages near the border, and so every every village should either have an army or have an army that's on a certain time distance from a neighboring village. Actually, they have slightly more complicated rule, and so there is a variant of this dominating set problem. Okay. So, but now let's think about the hitting set problem. And so we will assume that all the sets have small size. And now the claim is that there exists a kernel of the size given here. So that's our theorem. It's very easy, so I will not copy it. So there exists algorithm that in polynomial time prints a kernel of this size. So note that if D, So note that the size of the kernel does not depend on n, the size of our input. So, well, roughly, I mean, the size of the input is basically D times n. But if D is bigger than n, then Well, actually, I don't remember what we should do if DS, then there should be something true. We can throw away a lot of the elements. So maybe that's good for the seminar to think what to do. I don't know. Okay, but yeah, so input size is d times n, and the kernel only depends on oh wait, that's not a real kernel because k is unbounded. So yeah, so sorry, this is not a real kernel. Well, it's a real kernel. Yeah, so only if both d and k are parameters. But this was a homework exercise. Oh my God. Yeah, in the homework, it was k times d kernel. So I'm completely confused now. How can I miss it? It's very beautiful lemma, but now I realize it's completely stupid. Ah, but yeah, no, okay. No, this is a more general problem. Yeah, so sorry, the application to dominating set is stupid. But still, this is a solid application, the hitting set problem. Okay, but then this is a bit less interesting. So let's skip it. Yeah, uh, okay, then we go very fast. It's kind of beautiful, but I yeah, so I learned it from YouTube lecture, but I didn't think carefully. So yeah, I now realize. Okay, but then we will skip this one. Okay, and then we go to a very beautiful technique, which is called color coding. Uh, so this is these problems are probabilistically solvable. However, so our definition of FPT was with deterministic algorithm. We will now use probabilistic algorithms. However, almost all of these algorithms I'm aware of, they can be made deterministic using hash functions. But I'm not sure if I will explain this because, okay, this is kind of statistical. K-wise independent hashing, I'm not sure if you need to know what this is. But let us start with just the theory. So here we will study the longest path problem, which is connected to the Hamiltonian cycle problem. I explained it when people were entering. Okay. And so color coding, I will say something very general. So the idea is to fix a part of the solution by random guessing colors of things. And then in polynomial time, check whether this guess is good or not. So the guesses will be exponentially small probability to be right, but hopefully a good exponent. And if we do it many times, an exponential amount, then we still have reasonable probability to be right once. So that's, okay, this is abstract explanation. Let's do with an example. So we are given a big graph. And well, first let's do the input is a graph. So the longest path problem. Input is a graph and a number k. And then the question is there a path? So can you visit k nodes in a row, but exactly once in your path, like in the Hamiltonian path problem? So question exists path. So path usually means simple path of length k. Okay. And so there is algorithm in time. And here we will have 2e to the power k, poly n. So n is number of nodes in the graph, k is the length of the path. So state of the art is 1.6, something like this. But it's very complicated algorithm. That means that Hamiltonian cycle can be, so in dynamic programming, it was 2 to the power k. So people can improve a little bit. And we know that exponential time hypothesis says that we cannot have 2 to the small o of k. So at least exponential. So we cannot have 2 to the power k 0.9, for example, or square root of k. So if this were true, okay. Yes. So what's the idea of the algorithm? We will randomly assign, we will take k callers and randomly assign one of k callers to all of the nodes. And then we will check whether there exists a path with k different callers. So that's the advanced algorithm. Simple algorithm is if we check if there is a path with caller where the first node has caller 1, 2, 3, 4, and so on. And so let's take simple algorithm, which has a little bit worse runtime. Simple algorithm. So simple algorithm, make random callers, then check whether first node, so look, go over all the nodes with caller 1, and then check whether you can find a path where the second node has 2, 3, and so on. So which algorithm will you use to check it for each node? For each node with number 1, with caller 1. So how will you do it? Which? Yeah, BFS works. Breadth first search, so you make a list of. I think it's my first reflex would depth first search. But okay, yeah, breadth for also. No, you're right. It's equally good. So yeah. So just any algorithm. So simple algorithm. And so let's do a little example. So imagine that the input is this graph as usual, and then we do 3. And so then we randomly assign 1, 2, 3 to each of the nodes. For example, 1, 2, 2, 3, 1. And so then we start to search. We go over the node with 1 and we check 1, 2, 3. Yeah, this is very easy. It's already finished. If we have 2 here as well, then okay, then it's impossible. So we go here, 1, 2. So this is what would be a bad coloring. If we try the 2, yeah.
It's good. Why we just randomly color some?
Yeah, so this is the step. So we choose random colors and then we check if a path exists. But now we have very small chance of being right. So the idea is to repeat it many times. And then we want to be successful with probability 1/2.
Why we cannot just take one node and for neighbors?
Yeah, actually, thank you for question. It's a very good question. Why? So, okay, I answer your question later. Let's first go to even simpler question. Why not brute force generate all paths? Yeah, it will take long. So we need to try basically all subsets of size k. If we do like a tree where we built all the paths. So it will run in time n choose k, which will be basically n to the power k. It's really slow. So this runtime is much better. Okay. So, but then we need to also think about the probabilities, like how, oh, sorry, your question. Yeah.
Then color neighbors.
Okay, yeah. So you are doing kind of brute force search.
Not good, but it will work in parallel as we, for each node we color at the one time for one and the second neighbor. The first
Yeah,
and
so
second
you say let's color all the neighbors too. And then what we do with these neighbors? We color them 3.
they are neighbors.
Yeah,
And in one step.
so this will also be 3. But then, for example, can be a graph with diameter 3, for example, but with 10,000 nodes. It's because the one node is close to all of the nodes, and then you won't have any high numbers.
Okay, we need to find the maximum number of or no, the subset of size k or its maximum.
Yeah. For example, imagine the input is 4, and we do your plan. All the nodes are in distance 3. So we will never, yeah.
No. If we, for example, so for 3 nodes for the right, we have neighbor with 2 and 3.
Yeah.
For example, we can color the second node, the left one.
Yeah. But what you are doing is kind of optimizing searches in a direct way. And if I understand correctly and debug, you will have always such dependency if you analyze. So if you can give direct algorithm that has f of k poly n with this FPT, you should tell it's interesting. But you need to think very carefully because all techniques I'm aware of use color coding, some randomness, and then de-randomization. So it's not so obvious to. Okay. Yes. So now we have to think. Okay. So simple algorithm. So choose random colors and find path. Find colorful path. Find path with color 1 goes to 2 goes to 3 and so on, and repeat k to the power k times. Okay, so now why do I choose k to the power k times to repeat? So how do we calculate? So
the colors.
Yeah.
We need to color the nodes.
Yeah. So imagine that our path exists. So we have yes instances. Like here we have a path of length 4. So what is probability if we choose random color that this path has colors 1, 2, 3, 4, or 5? Yeah. So sorry, I should use k plus 1 colors. Okay. Let's see. I changed the question. Path of length k minus 1. Okay. So if we yeah. So what's the probability that k nodes of the path, this specific path, have colors 1, 2 up to k? Yeah, so I fix one specific path. So what is chance that the coloring is right? Yeah.
Maybe
Yeah, you're right. I can repeat.
This node into 1
Over k, yes. This node also 1 over k.
No, k minus 1 because we also.
No. For every node we do separately. We take random color. Yeah.
But we need to find triangle gray.
So for every node we roll a dice, and every k possibilities are equal. So it's possible that all the nodes in the graph have color 1.
And it is part with only one.
Yeah, and now we look at precisely one path. And the question is, what if our good path has colors 1 up to k? Yeah, exactly. 1 over k to the power k. Okay, and now we use general statistics observation. So if we want something to happen once, how many times should we, if something with probability p, so p is a small number, if we want it to happen at least once, how many times should we try? And the rule is that if we try 1 over p times, then with probability almost 1 over exponent 1, and so with probability almost exponent 1, so 1 over p repetitions. So we will have success with probability very close to exponent minus 1. Okay, let me write it. Yeah. Okay, let me write it more clearly. So if event has probability p, then after 1 over p, let's round up, repetitions, probability that event happens at least once is, so let's say exponent 1 minus 0 is at least something like this if p 0.1, for example. So why is it true? So there is famous formula 1 minus 1 over n to the power n is smaller than exponent minus 1. But people know this usually. So this is also true. Here is formula, but it also holds if we put minus here and minus here. But also if n is large, it will be very close to equality. So basically it should be like minus 1 minus 1 over n squared. So and this is will we so here we need to bound to prove this. We need to bound probability that event does not happen for 1 over p times. So probability that event does not happen the first time is 1 minus p. Probability that it doesn't not happen for 2 times is this probability. So each time it's independent repetition. So when we do 1 over p and then round up, then we can apply this formula. So this will be smaller than exponent minus 1. Oh, I should say 1 minus. So probability that it happens at least 1 is at least 1 minus exponent minus 1, which is this is 0. I forgot 27. So so it's more than 1/2. And then we don't need any assumption on p. Well, of course, smaller than 1. Okay, and so why are we happy with probability 1/2? If we then repeat 30 times, then we have probability 1 over 1 billion.
Mm-hmm.
So if you're worried about this, then you can be worried about meteorite falling on your head or something. Okay, you can do 60 times and then for sure it's your computer exploding for no reason will have bigger probability. Okay, so so that's the plan. So we calculated that guessing the right colors happens with probability k to the power minus k. So 1 over k to the power k. And this is why I say, let's repeat this k to the power k times, and then we're successful with probability more than 1/2. Okay. So this gives us algorithm, but what's the runtime of the algorithm? So for simple algorithm, find path, it runs in time k to the power k n of 1. But here we have something better. And so I already explained what is algorithm here. And so here we check whether path has colors 1, 2, 3, and so on. We can get this algorithm if we check if colors of the path are all different. So then, so imagine that we have bad luck and we have 1, 3, 4, 2, and 5, for example. Now, this is also a set of colors that also works if we have algorithm that checks whether colorful path exists. And so what could be now, but now we have a different, a harder task. So we go over all the nodes, but we need to check whether colorful path exists quite efficiently. And so you cannot do it in polynomial time in the number of nodes, but you can do it in time 2 to the power k poly. You can check whether a path exists. It's by dynamic programming. So yeah. So you can say, let's try all orders. And so how long will this take? So you say, let's take all permutations of k colors and then apply previous algorithm, depth first or breadth first search on all permutations. So what will be the runtime? A very good question. So what will be, how many permutations do we have of k colors? Yeah, it's k factorial, right? So k times k minus 1 minus 2 and so on. And so how is k factorial? So there is this rule, it's approximately equal to k over e to the power k. It's Stirling formula. So it's like k to the power k. So it's just basically the same as easy algorithm. It's only a little bit better. So we're more ambitious. So how can we get? And so checking what color, how can we get 2 to the power k? And so by the way, this 2 will be this 2. We also get e to the power k. It has to do with probability. So how do we do it? Checking whether colorful path exists. It's by dynamic programming. So it means we build table. So you use in other courses, I guess. Dynamic. It's not the first time, right?
Yes.
Yeah. So we will build tables. So how will the table look like? So the idea is to go over all, so we will make a table and then every column. So the columns will be 1 till k. And the nodes will be sets of colors and first no, and no, so pairs. So here we will have node and as sets as all of colors 1 to k. In column 1, we have singleton. In color 2, so the colors will represent, the set of colors will represent colors that we already used. So for every node, so we will construct a path. So in every row, we think about in row I, we think about the 8th node of our path. So we think that a given node is the 8th node, and the set of colors will be the colors that were used before this node. So in the ith row, S will consist precisely out of I colors, and we go over all the sets of I colors. in this row. And then it's easy. And so if we have a node V and a set S of colors S, so how can we construct it if we have the previous rows? And so remember, we are building a path. And now we think that V will be the I, so this column I. And we have already filled the table here. It's clear what is the table. And so how many rows do we have? And we will have at most number of nodes times number of subsets. So basically in row I, we will have number of subsets will be K choose I. Number of I element subs. So in row I here, number of nodes times number of subsets of size A of colors. Okay, so now let us look to, okay, I can call I minus 1 if this is the previous, if you're talking about the previous column, of course. Okay, now we are in set, we want to fill in set V. So is there a path for which the ith node is V? And all previous and all colors used so far are in S. So that's our question to fill in one cell. So how do we do it? Well, we check. We think that we go over all colors in S to be the last used color. So we drop, for example, color 1. Let's say that V has color. So we check the color of V, sorry. We check the color of V. If V is not in S, we say no solution. If V is in S, then we remove color V from S and we check whether, so we check whether for every neighbor of V, whether U S minus color of V is in the table. And if there is such a neighbor, then we say yes here. Otherwise, we say no. And then we build the whole table, and then we check whether the last column has a yes. So it's basic solution for dynamic programming. And so the size of table is 2 to the power k poly n. And building every cell takes time of the degree. So it's also this time. Okay. So now we have understood checking one color choice takes this time. Now we need to think how many repetitions do we need to get probability 1/2. So now we have to think about what is probability that a fixed path gets all different colors. And so before we had 1 over k to the power k probability. Now we get something very similar. But now we should listen to your formula. So, okay. So for the first color, so let's fix a path. And we have to check probability that every node in the path has different colors. So let us think about the first node. Any color is good, right? So we have 1. Then the second node. How many colors are good? Yeah, k minus 1 divided by k. Then third node. Similar, right? And so on. And so in the end, we have 1 over k. For the last node, only one chance. So this is equal to k minus 1. Well, I can write k factorial. So I say 1 is just k over k. And now it's easy. K factorial over k to the power k. So that's our probability. Now we want to simplify this. And I already give hint from Stirling's formula. So, let us, but a nice way to think about this is about Taylor formula. So, remember from maybe high school or elsewhere, a to the power k it's equal to so sum for a to the power x, x to the power k, k factorial. And so we sum k starts from 0 to infinity. So maybe you have seen this formula. It's very famous formula. And this has good consequence. It implies that a to the power k must be bigger than k to the power k divided by k factorial. And actually, it's pretty good approximation. So in all the sum, the most important term is when we set for x equal k will be the term here with x equal k. And so this is precisely what we need. We need the probability. So where it is, k factorial divided by k is bigger than something. And so this something, to get it, we flip over everything. And so we know it's bigger than e to the power minus k. Yeah, and well, not only we get lower bound, even a pretty good one. Don't try to improve. Like you can divide it by square root k or something. It's the best you can do. So ask machine learning people, they use it all the time. Okay, so now we understand how many repetitions we need, right? It is e to the power k repetitions, and then we are better. So here we set p equal to e to the power minus k, so that many repetitions. And so here we have our two values, 2 to the power k poly n times e to the power k. So this is precisely what we have here. So it's color coding algorithm. Okay, so now we are 5 minutes after time. And then I promised that there was very short topic to check graph isomorphism. It's pain in the ass if you need it, but color coding is, yeah, so there is Naughty package that gives very good algorithms. Like some professor all the time spent on this package Naughty. I mean, he's now very old, but finally, yeah, now it works very well. And it was for old computers in C. So if you have to do nasty things with graphs, then you should Google this one. Okay, but there is very nice algorithm. And so what is the problem? You get a small graph and you want to find whether the small graph is present inside big graph. So a special case of this problem is clique problem. And so you get a clique, a fully connected graph. You want to know whether it's present in the other graph. And so it works by color coding. Provided, so the parameter will be the degree of the graph. So it's a very big, for example, also a Hamiltonian path problem, a special case of graph isomorphism. So you want to know whether a path of length k of length n exists inside your graph. And so what is the trick here? We will use color coding with two colors. Well, let me write the problem first. The input is two graphs. So graph A, graphs H and G. And the question is, find, so is H subgraph of G? So not induced subgraph. So, I mean, there can be extra. It's H subgraph G, and the parameter, oh, I forgot to write it, is number of nodes in H. The size of H. Okay, and so our claim is that this is an FPT, so solvable. Sorry. what do I say? Not, yeah, number of nodes and max degree of G, sorry, 2 parameters. And it's solvable in time. And so it is k to the power d and to the power of 1. Maybe d plus 1. We will analyze it soon. So algorithm is very simple. We will use 2 colors. So we color in 2 colors, and then say red and green. And then we check whether, so we will remove all the red nodes, and then green graph will have connected components. And then we check whether one of the components is isomorphic with H. So for graph isomorphism, there is a very good, well, theoretically good algorithm, but we can use slow algorithm as well because this is huge bound. So we color, so color red and green. And then is the idea that if H is present in G, and all the nodes of this H are exactly equal, are green, and all the neighbors are red, then this graph H will be present in your graph as an isolated component. So after we do red-green coloring, we drop the nodes, and then we have a list of connected components. We take each connected component and check isomorphism with brute force algorithm. So if k is number of nodes in the graph, then brute force is k factorial. But there is a better algorithm that runs in k log k. So I should add. So the runtime is, well, actually, I don't know, something like this. K to the power d plus order k and of 1 with a good algorithm. Okay, so now we just have to check how many repetitions that we need. And so what is the probability that indeed appears as connected component? So graph has, so 2 graphs, A prime and H with k nodes to check whether they isomorphism. That's what I just said, I'm repeating. So it takes this time. K to the power log k, it explains why this is, sorry, log k. So this explains this part of the exponent. It's checking isomorphism once. Number of components is polynomial in this size. Okay, now how many times do we need to guess? For this, we need to know probability that our guess is correct. So we have a graph, and inside, so we have some big graph, and here inside is graph H. And so we need the k nodes, so k nodes. We need all of them to be green, but we need a little bit more. We need all of the neighbors of these nodes to be red. So that H appears as connected component. But note that degree is, the degree is parameter. So what is probability that we guess correct, the 2 colors correct? It is 2 to the power minus k minus d times k, right? 2 to the power k, that all nodes of H are green. And then how many neighbors are there? Since all nodes have the most degree d, graph H has at most dk neighbors, and all of them have to be red. So yeah, I lied again to you. So it will, let's write. Okay. Actually, what I wrote first, and then I said it was wrong, but yeah. Okay. So this will be our running time because probably, but there is a k here. Our time is 2 to the power kd plus k. So finally, I got it right. So it's also a long day for me. So solvable in this time. So this is pretty simple, hopefully useful algorithm. So it's easy to implement, right? Well, I mean, given that you have something like you can use Naughty or whatever package for isomorphism, so you have to call it, it's a bit annoying. But there is binding in Python and C++. Okay, that's long lecture, but we started late, so it's only little long lecture. And then there is seminar, there are just 4 exercises. It's not too much, but we didn't cover only 3 exercises because decomposition, how it's called, flower decomposition, I dropped. Okay, so see you next week. Next week is tree decomposition. Definitely optional lecture. So something very specific. So there's a graph who look a bit like a tree. For example, a cycle looks a bit like a path. So if you pair up the nodes, you can like cover with the path. So the idea is that if you can make a graph similar like a tree by grouping the nodes, then all the problems that are NP hard become easy. And this is like a huge business for research. I don't know what's happening in companies. So and then there is a cool theorem how you can know the tree width, for example, of a grid with helicopter and criminals. And tree width is how many policemen you need to capture the bandit. Okay, that's for next time. Okay, so see you next well, maybe in seminar. Okay, bye.